We've been waiting for the images from the James Webb Space Telescope for years, and they're finally here. This video is not only going to show you a new window on the universe and gush about how lovely they are, but show you in simple terms what this incredible telescope is revealing, what it's discovering, and why that tells us where we came from and if we're alone in the universe. And because we've waited a week for the sensationalism to die down, there's now more data and more to talk about, with images of galaxies, star-forming regions, the planet Jupiter and its rings, deep galaxy fields, and the least showy but perhaps most impressive of them all, the contents of the atmosphere of a planet 2 million times further away than Pluto. But get involved. Tell us what you think about the James Webb Space Telescope. What's the best image you've seen from it? Has it been worth the wait? What are you looking forward to finding out? Drop your thoughts in the comments below. We read and respond to every sensible one. The views we're now getting on the universe are truly incredible and paradigm-changing stuff that we're going to bring down to Earth for you. But first, to show that we're not bandwagon jumping JWST gravy train peddlers, Paul, you're still not impressed, are you?
Oh, well, no. I mean, No, I am impressed. But I think there's so much more to come, and I think the problem is a lot of it is data. This is all about the data, and it's going to be less about the images. And I think one of the issues they're going to have to constantly deal with JWST is that the images. I think when we talk on our Kushner back channel is actually the images they're better than Hubble. They are better than Hubble, but they ain't that much better really in the big scheme of things. We've got so used to Hubble, and even some of the stuff coming out of the European Southern Observatory and Keck and things like that. The images are so spectacular. Actually, they're just more spectacular images. They're just. I think they're like putting on a better pair of glasses. So it's to say similar images, slightly better, slightly sharper, a little bit more detail. So for the lay person looking at the images, it's just almost like kind of service as normal. It's like, oh, it's just morally spectacular astronomy images that everyone's got used to and everyone's kind of happy with, and they're beautiful and stunning. But I mean, the deep field thing was. It's not that much different to the deep field that Hubble took in the kind of that initial. Yes, it is. I mean, to the astronomer, you're looking and go, oh wow, that's amazing. There's so much more there. There's loads more.
Yeah.
But actually, you can see that a lot of the same galaxies are just sharper, clearer.
But I think you made a really good point right at the beginning when you said that JWST is about the data.
Exactly.
Because in its first year of operations, 70% of its time is dedicated to spectroscopy. And that's not going to produce images.
No.
That is.
Oh, is it? I wasn't aware of that. 70% of its time. So it is pure data for the astronomers that have been waiting for this.
It's going to be numbers and graphs.
Yeah, it is. Yeah. It's for finding redshift. It's for figuring out compositions. It's for temperatures and densities and all the wonderful science stuff. So it's most of its time in its first year is actually going to be spent doing that hardcore work. It's just at the minute the things which are popping out of the telescope quite quickly are the images. And yes, okay, we knew that the resolution was going to be on par with Hubble's, but it's what's sort of hidden in these images, which,
and in a sense, what I really want to mention, and I'm not sure how much this has been said, is that the fact that we are getting better resolution than optical with an infrared telescope, given the physics of this, is astounding. A longer wavelength, poorer resolution. So that just shows how fantastic this telescope is.
Yeah. And I think they've missed a slight trick with the whole colour scheme that they've gone for, because they've essentially applied the Hubble palette to JWST.
Yeah. Yes.
And this is fooling people into thinking that, it's just basically the same as Hubble, when it's not, because it's infrared. It's light that we cannot see.
You mentioned about should this have a different palette, the JWST palette, and I think it should have done, just so that you can see the difference.
Yeah, I was really hoping
future,
it was
you
going to
won't
be
know
red.
when you see an image, whether it's a JWST image or a Hubble image, unless you know.
I was hoping it was going to be like a colour scheme that sort of favours reds as a sort of nod to like infrared, so like pinks and purples and stuff like that. But no, they've kind of gone for a Hubble palette, and I think then that makes it's easy to confuse it with Hubble images and stuff like that.
It's like one of my favourite series of images in astronomy is the images of M31 that are taken in different wavelengths.
Oh,
and
yeah.
They're just stunning images. They've been around for years. They've been around for years and years. And there's radio ones and X-ray and infrared but they're all in different palettes. They're all been presented in different ways. So you see different things instantly. You can just sort of hold them. I've used them in talks where you hold up these images of them and say, like, this is the same thing, but God, it's a completely different thing you're seeing. There's stuff here that you can't see in this one. And you're right. I think they missed a trick there, that they could have really highlighted how different and what different wavelengths are being used with a different palette, with a different emphasis on the image.
But let's talk about what we have seen.
That's literally what I was going to say, Rob. I was going to literally say, let's talk about what we've talked about. But talk about what we talked about. No, talk about what we've seen. Yeah. So I think, the first on my list is Stephan's Quintet, which is a really nice target because, of course, you can look at this with backyard telescopes. You can do images of this yourself. And Stephan's Quintet is one of the first galaxy groups that was ever discovered. And, of course, it's called a quintet because there are 5 galaxies. When you initially look at the image, you might be fooled into thinking that there's only 4, but look a little bit closer and you'll see that 2 of them are actually merging. They're very, very close together. And, of course, one of them is actually a foreground galaxy. So it's only 4 of the galaxies which are interacting. The one when you look at the images, which is sort of on the left towards the top, that one's a foreground galaxy. And, you look at the Hubble images and you're like, oh, yeah, look at this. Galaxies interacting. Cool. There's all sorts of distortions and stuff. But there's 2 really striking features about this image with the JWST version is that if you look towards the right of the image and in the middle, you can just suddenly see all of this shocked gas which has been heated due to the galaxies colliding. And you kind of get a hint of it in the Hubble image, but of course in the infrared you can trace the dust that's mixed in with the gas, and so you can see this activity, and it just unveils another level of galaxy evolution and interaction which we didn't see before, and that was really exciting. And then the second aspect, which is something that I'm going to come back to a lot, is that when you look at these JWST images, there's just so many galaxies in the background. Yeah, they're just there. There's just all these tiny little blobs, and they're just
it's just something
hello.
You get for free, isn't it? It's like, hello, I'm a galaxy. I just happen to be sitting here in the background.
And these are not in the Hubble images, and that is one of the defining differences between like Hubble and JWST images. It's not stars in the background, it's galaxies, and they are
entire
far
away.
Thousands
of them.
What I loved from the amateur astronomy perspective is when that image was released, you could see it right across amateur astronomy. People going, I've got to go out and look at that one now myself.
Yes.
And people just, for the following week, certainly here in the UK, there were just loads of people imaging it, sketching it, observing it, because it was like, wow, this is actually something that we can see, and comparing their images. With an amateur telescope
in your own back garden, that's something you can see. Obviously, clearly not in the same resolution, but it's there for you to see.
But it is there,
Yeah.
And then next up on my list is, I think, the one which has really captured everyone's hearts, and that is the one of the Carina Nebula. And that one is glorious. There's no way to deny it. Like all of those stars popping out in the nebula, because of course now we're looking in the infrared, we're peering through some of this gas and dust, and we're able to reveal so many more of these young newborn stars which are forming in the Carina Nebula. But I think what this one really highlights as well is just the extra resolution and the detail that we are getting from JWST, because you can see so much more. There's so many more fine kind of twists and twirls going through the nebula and stuff like that.
I think actually that contrast between what Hubble's taken and what JWST's taken is highlighted so much more with the Carina Nebula, because you can see the resolution just pops out because you're seeing such a big single image that's got so much detail to it. This is where you see all that sinewy gas and dust illuminated and the darker areas. It's just such
You do
good
feel
contrast.
that was the image. Thinking of that, the original announcement, that's the one they perhaps should have led with.
Yeah,
because that was the one that definitely has had the most public impact, because it just
I have seen
spectacular
puzzles created out of that image and clothing, and it's just going nuts.
It's already on t-shirts and skirts and
that's
scarves
great
and also I've seen it kind of
Yeah.
already tweeted, people going like, oh, I've got a skirt of it and I've got a t-shirt of it. Already it's going to be an iconic. It's like some of those Hubble images from like 20 years ago that first appeared, and people were printing them on things and posters. That's going to be one of those. That's that first.
Yeah, if there's
JWST
anybody
image,
listening to this and watching this that hasn't got that as their screensaver, I imagine there's only about 3 of them.
Yeah, and just some interesting details about the image itself. If you're wondering why it's sort of orange at the bottom and blue on the top, so it always looks like the sky and the beach, as it were. The blue at the top is actually where a hole has been carved in the nebula by the intense ultraviolet radiation from some really massive young stars, which are just out of shot. You can see some of the diffraction spikes at the top of the image, but this hole has kind of been carved out by the ultraviolet light, their enormous stellar winds, all of this. And then what was the other thing I was going to say about? Nope,
The whole
it's gone.
thing is just wonderful.
It's gone out my brain.
So it's so astonishing. It's literally blitzed your mind.
I know it has, because I was
just
like
blown
picturing it in my
your-
mind's eye, and then I was just like kind of getting lost in it.
You had your Brian Cox moment. You went stars.
I was like, oh, stars. Yeah, I did.
And given how many TV interviews you've probably done on this recently, I'm surprised that you've forgotten what your next point was. But shall we move on to the deep field image then? Because this is one where I think if we'd have used the Carina Nebula, if NASA and ESA had used the Carina Nebula as that contrast with Hubble images, this deep field image is a good one to have as a contrast image to show, this, we've taken this with the Hubble and this is how much more we can see. And astronomers will love this because there's so much more detail in there they'll be able to take from this. But that was one unnecessary step, I think. I think what they should have done with this is just gone even deeper and shown that what we can now see with this telescope, how much further back we can go, that we can now see galaxies and stars that we couldn't have seen with the Hubble.
I think actually this image has got more exciting in the couple of weeks since the announcement, hasn't it? Because I think there was another announcement today of yet sort of another galaxy that's potentially just that little bit further than the one that they were talking about like 3 days ago that came out in paper. There's someone's going like, no, actually, there's one here that's even further. And
they're releasing the data as well, so that, again, citizen scientists and amateurs can pour through it as well and find things.
Exactly. And there's that great, the girlfriend meme with the bloke looking over his shoulder.
Yeah.
And literally, it was one. It was like the girlfriend's got like Z14 on her, and the girl he's looking at's got Z16.3, and he's all going, it's like astronomers going, ooh. And it was that kind of, it's within a couple of weeks we were the boundary that kind of how far back it's being pushed and pushed and pushed and pushed.
And that's not just from this deep field. We've now, of course, because it's been doing science operations for 2 weeks roughly, and so more fields, that data is being downloaded. But I think one of the most astonishing things about the SMAX 0723, which is the deep field, is that the Hubble version was about 10 days of exposures.
Yes, good point.
The James Webb Space Telescopes was just 12 and a half hours.
So how much more science can you do when
it does an actual deep field?
You don't need to image anywhere near as long.
When it does 10 days, like imagine doing a 10-day version. It's just it's going to be, and that's where that's got more exciting. I think it wasn't the image to lead with. I think they made that was a mistake visually, but in terms of what it's actually saying and doing and the data that's coming, the related data, I think is actually far more exciting. That's really demonstrating what that scope can do.
But carrying on with all of these, Z equals 12, Z equals 14, Z equals 16, of course, where the Z is referring to redshift. And the higher the number, the further back in time that we're looking. Just to highlight these, you mentioned that one that was like Z equals 16.7, which is one that's come out today as we're recording. And that's less than 250 million years after the Big Bang.
Yeah, bonkers. That's just...
really, and we didn't even know if galaxies would exist at this point.
Yeah. There was no chance that Hubble could have imaged this.
No.
And I think that's the kind of I don't want to keep coming back to media fails, but I think that's where, or rather NASA ESA communication fails. But I think that's the thing that's really going to capture the public imagination, that we can see things with this that no instrument has ever enabled us to see. This is the real birth of matter in the universe, and the things, the massive objects that enable life to actually exist, and we're actually being able to see this crucible of for want of a better word, creation.
It's really, I mean, this is what was being talked. This is why it was kind of really annoying with JWST, because we've known this is what the scope was designed to do. This was its capability. This is what the aim was. And the whole delay was just this is what we want. It's not the pretty images in the end.
It's the blobs.
Hard data on these tiny blobs that we can't see, that we guess are there. We all the theories are saying they're there. They're beyond Hubble's capability. They're beyond European Southern Observatory's capabilities. They're there. We need a scope to do it, and that's what was getting really irritating with waiting for this scope, because we know this thing's going to do amazing stuff if it all worked, and it's just worked beautifully. Absolutely.
Which is why, for me, the most exciting thing has been the spectra that we got from WASP. I forget the name of the star, but
before we move on, I just have to put one more thing in, because it's a slight Debbie Downer. But all of these redshifts that are being popped out for these galaxies, these are just from photometry. We need spectroscopy to confirm them. So lots of these are being shouted about, it's 250 million years after the Big Bang, 200 million years after the Big Bang. Until they have spectroscopy, and also until these papers are peer-reviewed by the rest of the scientific community, they are just candidates. They're not
and what
firm
we'll find
discoveries.
Is they're all from a week last Thursday. So
yes. So just to kind of throw that little caveat in, I am sure that some of these are going to turn out to be exactly what we thought they were. But just until we've got that spectroscopy, we have to throw a little bit of caution.
You want that confirmation in there. Before we say it with any certainty.
You and your science. And
I know, I'm bringing everyone down, ruining it with facts. I'm sorry.
Anyway, before I was rudely interrupted.
I know, I'm sorry. I had to
getting
get
the spectra from exoplanet atmospheres. We're talking about atmospheres from planets that are 2 million miles further away from us than Pluto are. If my maths are right that I did earlier today. Being able to peer into the atmospheres of those as they're passing in front of their star, and being able to deduce what's in there and show that there's water in there, in that atmosphere. That, for me, is fantastic, because all that is doing is showing us that we know we can do this now, and every time we go to a different star system, we're going to be able to peer into the atmospheres of the planets that are in there that we already know do a transit in front of their star, and we're going to get such a rich picture of all of these star systems. And already I saw today that the TRAPPIST-1 system, which is the most exciting system for most astronomers, is already being looked at. So,
are they doing it already?
Doesn't know, doing it already. The data is already starting to come out on that one. Of course,
we knew it was on the
had
list.
to.
Well, I knew it was on the list because I had a look at what it was doing in its first year, so I knew it, but I didn't realise they were going to be doing it so soon. And
they
the TRAPPIST,
don't they?
How often? I mean, this is the really exciting. This is the other really exciting thing about JWST. We have talked about this for years. I mean, this podcast has been going for over 10 years now.
Yeah.
And literally, we have probably talked about the new generation of telescopes, including JWST, but also all the new ground super telescope. We've talked about this capability of looking into the atmospheres of these exoplanets for years. Probably most of the podcast history, we've talked about this. Yeah. It's coming. We're going to have this capability to go, there's that in this atmosphere, and there's that gas, and we will find those traces of methane and things like that, and it will just be very exciting.
Yeah. And just for a little bit of context, we care about the TRAPPIST-1 system so much because it's only 40 light years away. It is a system of multiple rocky, Earth-sized, roughly, planets. I think there's 7 of them now. And they're orbiting a small red dwarf star, so much smaller than the sun, cooler than the sun, but orbiting much closer in. So several of them are actually in their planet's habitable zone. So this is super exciting because 40 light years away means that within the span of a human lifetime, we could send a message and we could get it back. You know, so looking at their atmospheres is why astronomers are like losing their minds over this capability with JWST.
You see, that is going to be a result that will be worth screaming and shouting and crying about when that comes, because that
it's the big one,
properly earth-shattering.
It's the big unanswered question, and it's the most ground-shattering question we could have answered. I can't think of a question that we could have answered that would be bigger than that. Is there life out there?
Yeah.
You know, and even beyond that, is there intelligent life out there? Because because most stars are so far away from us that even if we suspected there was life there, it would take so long to get the message there and get a message back.
It's literally
and then, of course,
one of
all
those
the questions around, do you want that?
It's literally one of the most fundamental questions of astronomy and science, isn't it? It's, you know, I say this to kids, it's like, you know, the big questions of astronomy aren't like what are stars or what are planets and things like that. It's, you know, how did the universe form?
Yeah.
Are we alone? They literally, there's like that, you know, that's the kind of key questions of astronomy and science we want answered. Is like,
in a sense, I think all the questions in astronomy are all just building up to that one question of, are we alone?
Completely. It's very
and science
exciting.
is the only thing that's going to tell us that. Astronomy is the only thing that's going to tell us that, potentially.
I would like
Unless they turn up on our doorstep.
With the images, I'd like to give a big shout out to the Jupiter image. I loved the Jupiter image, which was not one of the like kind of, you know, big official ones. It was like one of the test images where they wanted to see whether they could see things close to a bright object. So they picked Jupiter.
And is that a bright object in the
It's a bright object, exactly. So they pointed it at Jupiter to see if it, you know, see the moons and see the ring and everything. And it was just there was such fabulous kind of detail and sort of interesting stuff in that image for what was just a kind of almost throwaway test image. I loved
and in
it.
one
It
of
was such a brilliant image.
I can't remember which wavelength it is, but one of the images, it kind of looks like Jupiter is bulging at the north and south poles, and that is, they think, infrared aurora.
Yeah,
exactly.
So it was like interesting stuff was revealed just from a kind of
a test
throwaway
image.
test image.
Yeah.
Which was that's the stuff I get excited about, because that was different. That was really kind of, that was JWST to me. That was like, that's exciting.
Yeah.
But of course, it's showing us what benefit it's going to be able to give us to things like Trojan asteroids potentially, or other asteroids in the asteroid belt, and maybe even near Earth objects that'll be able to detect those because of the heat difference. Even though they're really small, it may well be able to pick things out like that. I don't know whether it'll get a lot of time doing that, but because there's so much, you know, cosmology it can be doing. Yeah. But it just shows. We've mentioned so many times before when we've been talking about the science of the instruments and talking about how this is kind of like an omni telescope. It does a bit or a lot of everything, and this just shows that going from you know, rings around Jupiter all the way out to the very earliest, the earliest galaxies.
Yeah, but as part of their kind of looking at planets in our solar system and asteroids tests, they discovered that they can actually track objects which are moving twice as fast as they were originally hoping. So it just opens up a whole new level of like asteroids and comets that can now be explored, because they know that the telescope can track and still produce quality science while going at such speeds.
What I love is that at almost every point this telescope is exceeding expectations. That's what I love. Like every aspect, from its launch where they saved all that fuel and it was in such a perfect launch, and it can now go for a longer mission. And to even the micrometeorite which hit one of the mirrors, and actually it's done much less damage than they ever thought that would do. They you know, that was really unlucky that happened so early on, but actually it's done far less damage than they thought. And And just every little thing, it seems to be exceeding its expectations everywhere. And it's
and we do a lot of criticising of NASA, but I think on this one it's a case of well done NASA, well done Northrop Grumman, well done everybody who's been involved in this Canadian Space Agency, ESA. It's a wonderful, wonderful telescope that you've created there. And when people from NASA were saying in the last probably month while they were going through all the test phases, were saying it is actually going to exceed all expectations. And then we heard that, like you said, Paul, that the Ariane rocket had got it into an orbit that means that it's going to extend its lifetime. Well, probably double, if not quadruple its lifetime. You know, it's probably going to have 20 years of life now rather than the 5 originally expected. Just well done to everybody. This is a phenomenal success.
It's just brilliant. It's just brilliant. I cannot wait for some of this data that's coming down already.
Yeah.
It's just so much fun.
And I do have a nice little interesting story in terms of how it's exceeding expectations. Because I had my graduation a few days ago and I was chatting to my friend Liz. Now, Liz has continued in active astronomy in the sense of she's doing a postdoc out in Germany. So it was really nice to see her because I hadn't seen her for a while. And she is part of the FANGS collaboration, which is a great name. And do you remember that image that was going around about that kind of like purple swirl of the center of a galaxy and people like losing their minds because they were like, oh God, it's like a demon galaxy or something. Did you see that? It was all like, it was looking at the gas and the dust emission in this galaxy. Well, that was from the FANGS collaboration and they didn't actually release it because someone, so there's some slightly dodgy stuff happening with JWST data because the FANGS collaboration had this data, but of course, because it's an early science project, the data is just released out to the community. And so someone, just a person, was just kind of trawling through the JWST data, saying, oh, what has it been having a look at? Found the images and went, oh my God, and just kind of put them on Twitter, and it completely went viral before the team themselves has had a chance to properly analyse it and look at it.
Wow.
Yeah, so now
I think there's going to be a lot more of that as well because they are releasing so much data.
Yeah, and people are a lot more savvy now. They know where things are and they know how to have a look at them. And so now, as a consequence of that, they're setting up a FANGS sort of like Twitter so that when their stuff comes through, they can be like, it's ours, pay attention to us. But the other aspect of the story is that because JWST is exceeding expectations, this is actually causing problems for scientists because they're having to go back into their proposals and actually sort of reduce their exposure time because the telescope is so sensitive that if they stuck to their original plan, it would like overexpose the objects that they were trying to look at. So actually the fact that it's so good is causing science problems. Things are having to be revised all the time.
There's a problem you don't often have.
I'd like less telescope time, please.
It's looking too hard. You need less time. But then I suppose potentially that means if they get into that idea that actually they don't need as much time, that means they can look at more things. Overall,
exactly. So more projects can be looked at. Exactly. Really but I just thought that was an interesting little anecdote, something a little bit different that hopefully people sort of haven't heard elsewhere. A nice little Awesome Astronomy exclusive. Thanks to my friend Liz. Maybe she's watching. Hi, Liz.
So I guess the only other thing left to talk about is the Southern Ring Nebula, isn't it?
Yeah, which, like, the images of the nebula were spectacular, don't get me wrong, there's loads of fantastic detail, all sorts of ripples and structure. But the thing for me about the Southern Ring Nebula was that we're looking at a glorious planetary nebula, the eventual fate of the sun. And yet, there are still galaxies just like creeping, popping through this nebula, like, hello. There's like one which is just like this line. And then there's like a couple of face-on spirals, and they're just like, cooey. It's just, get away.
This is going to be every single JWST image, isn't it? It's going to be just like, it will take an image of something, and it's solar system, and they'll be just like, hello, galaxies.
Everything's being photobombed by distant galaxies. They'll be like, get away, you first galaxies that ever emerged. We're sick of seeing you.
I'm trying to look at Pluto. Go away.
And this is just because it's an infrared space telescope, it is just absolutely poised for looking at those distant galaxies, and that's where their starlight is. It's been redshifted into the infrared. So instead of screaming at us in the optical, when we point our telescopes to the skies, like our backyard telescopes, they're now screaming in the infrared in the distant universe, and JWST can't help but see them. So it's
if you're going to design a telescope to see that stuff, it's designed specifically for that, then we can't be upset if every image just happens to have those peeping out in the background everywhere.
Yeah.
But what do you think? Drop your thoughts in the comments below. And if you haven't already, give us a like and subscribe to the channel. It really does help us out. We've got tons more videos here on JWST, SpaceX, Artemis and NASA missions. The list goes on with a new video every Friday. So subscribe to the channel and get more spacey goodness every week.